Okay. As you know, today is the second lecture for exam 3. And so we're going to go through a very, very major application of double integrals. It's kind of cool because we'll be able to answer some questions from the past. Like, in other words, we'll be able to answer some geometry questions that we may not have known the answer to. And that is because we're going to figure out how to find surface area. And I don't mean surface area of a geometric object like a cube or something. I mean surface area of an actual physical surface. So again, I'm making my bed and I'm fluffing the blanket and I let go of the blanket in the air and I've got hills and valleys and I do a freeze frame. I have this thing and now I want to calculate the surface area of this blanket based on the hills and the valleys and some sort of description of the function. Now, that's not a trivial thing. That's actually, conceptually, that can be quite difficult. So let me give you kind of the generic picture. Oh, I got a lot of pens over here. So my generic picture is going to look something like this. I've got, you guys, supposed to represent a surface right there. And then what I want to do, I want to find the area of this. Now, here's the tricky thing about area. If I take a piece of paper and I say, what's the area of this? The flat piece of paper, you go, that's a piece of cake. No issues at all. So what I'm going to do is hold the paper horizontally and imagine that there's a shadow that's created. Okay. Now the shadow on the floor should be exactly the same as the paper itself. I think that's pretty easy to see. But what if I tilt the paper? What if I tilt the paper like this? Now the shadow on the floor is going to be only a small fraction of the area because I've tilted it. So if this paper is only 2 inches going across this way, then its shadow on the floor is going to be a very small rectangle. Okay. And if I tilt the paper further, maybe it's just a parallelogram, but again, the shadow is smaller than the thing that I'm looking for itself. So I figured out a way years ago to explain what's going on here. I have a surface, and so what I want to do is divide it up into a whole bunch of little sections and think of sending their shadows to the floor. Now, what do the sections look like? Well, I have a friend years ago who had a kiosk, I think it was in Fashion Valley, and what she did was people brought in their cell phones and she put little sequins all over them. Like she blinged their cell phones, and people would pay a lot of money for this. I don't know why. And she put little sequins all over the cell phone. So I'm going to put little sequins all over this thing. And the sequins are going to be little, it could be little rectangles, little parallelograms, whatever you want them to be. But the whole thing is going to be covered with little pieces like that. Now, the sequins themselves are flat. But as I cover the surface, if I found the area of each of the sequins and added them up, then we'd say that's a reasonable estimation of the area of the surface, especially if the sequins are very, very small. So what I want to do is say, okay, I've got this sequin, but it's at an angle. So when I project it onto the XY plane, okay, first of all, if I project my entire surface onto the XY plane, it's going to be this. Okay, this is my region in the XY plane. I'm projecting the entire surface down. This is the shadow. This is the two-dimensional shadow it's creating. So the area of this clearly is a lot smaller than the area of this. But now that little guy that I just projected down, what is it going to look like? Well, I'm going to project it down in such a way that it's these pieces, oops, that's terrible. They are parallel to the axes because that's how I'm going to subdivide the top. So when I project it down, it's going to be parallel to the axes. And that piece right there, this will be delta xi in length. This will be delta yj in length. So it's safe to say that this area right there, which we will call the ijth area, would be delta xi times delta yj. Okay, it's pretty safe to see. I'm going to have a lot of these. So as I subdivide this with my sequins, all in rows and columns, each sequin is going to project down here. Now, if I find the area of that piece there, which I just did, that can't equal the area of that piece unless this piece was absolutely horizontal. Okay, if this piece is horizontal, like I showed with a piece of paper, the shadow would be the same size. But think of this piece as an angle. So what I need to do is figure out the appropriate multiplier. Whatever this area is, I'm going to need to multiply it by something to get the same area as that thing is there. Okay, so that's kind of our first goal here. Okay, hopefully that makes sense to everybody. So in order to find that area, I want to go back up to the top here, and I want you to think about this as being, think of this as being a vector. And think of this as being a vector. Now this vector will be in the X direction. This vector will be in the Y direction, except because it has an angle, it will also have some Z stuff as well. So for lack of a better name, let's call this vector vector A, and let's call this vector vector B. And now what I need to do is figure out how to describe A and B. And here's the reason I want to think about it in terms of a vector, because I know something about that area in terms of the vector, right? Cross product, things of that nature. You go, oh, I know that stuff. So what I need to do is figure out, first of all, what is the slope? So if I'm standing here and looking this way, there's the x-axis coming out at me, there's the y-axis, there's the z-axis. This vector here, right there, is only on the xz plane. This vector here is only on the yz plane. I don't have anything going in a different direction. So what I need to do is figure out the slope, because if I can figure out the slope on the xz plane, then I know exactly what to multiply it by. You see, if my tilt is like this, once I have the slope, then I know the multiplier exactly. So what would be the slope on the xz plane? The slope on the xz plane would be exactly the partial derivative with respect to x. That's what partials are. Okay, I know that. The partial derivative is the slope when remember, I'm holding y constant and only looking at x and z. So what would this be? This would be delta zi over delta xi. Change in z over change in x, rise over run. Okay, and I'm using the I because the x was I. So whatever that change in z was, divided by whatever that change in x was, that's exactly the slope in the on the xz plane. Now, what about the slope on the yz plane? Well, that would be the partial with respect to y, and that would be delta zj over delta yj. I'm using a different subscript because x and y are independent of each other. Okay, so far so good. Well, what does this tell me then? This tells me that delta zi is fx times delta xi. This tells me that delta zj is fy delta yj. And this will help me now so I can describe my A vector and my B vector. This is actually very, very simple at this point. I'm going to have to erase this in a minute. So what does that make my A vector? Well, remember, if my A vector is going to have a particular slope, okay, then basically whatever the x coordinate is and whatever the z coordinate is, the z coordinate over the x coordinate has to be exactly this slope. So let's describe A as delta xi 0, delta zi. Why 0? Because A, we said, lives on the xz plane. There is no y component. Similarly, my vector B would be 0, delta yj, delta zj, because that one lives entirely on the yz plane. And again, if I said, well, this vector lives on a plane. I mean, I am in 3D, but it lives on the xz plane. So the slope of this vector would just be this divided by this, which is just fx. Okay, there's my fx. And this one, this divided by this, that is just fy. That makes things a lot easier. So if I replace my delta z's with these guys, let me go ahead and erase. In fact, I'm going to erase all of this. Sorry, I need that space. Okay. So I'm going to rewrite my A and my B now. So now I'm going to write my A by replacing the delta z and the delta zj. So I'm going to have delta xi 0 fx delta xi. Again, that ensures that the slope here would be fx. My b vector is 0 delta yj fy delta yj. And like we said before, if I want to find the area now of that sequin, all I have to do is find the length of the cross product. And that would give me my multiplier. Okay. Remember, I wanted a multiplier because the thing on the XY plane is not big enough. Okay. And so we're going to see this. So if we do, we'll start with A cross B. I'm going to go ahead and erase this because I've already got it. So what is A cross B? Well, let's see. So that'd be negative fx delta xi times delta yj. So that would be negative fy delta xi delta yj. And finally, delta xi delta yj. Okay, that looks kind of scary, but you notice I have the same term in each position. So I'm going to factor that term out. Okay, I'm going to write it like this. Fx negative Fy 1 times delta Xi delta Yj. Now, delta Xi delta Yj is a positive quantity. Okay, because remember, if you're looking at my sequence, delta X and delta Y can't be negative in this context. So when I'm finding the length of my cross product, all I have to do is find the length of this and then just multiply it. This would be a scalar. And that would be the square of this would be fx squared. The square of this would be fy squared. The square of this would be 1, all under the square root, times delta xi delta yj. This is my multiplier. Remember, the area on the xy plane, when I did my projection downwards, the area was this. What we needed to do is figure out the area of the sequin, the angled sequin that projected down. We needed to figure out what is the appropriate multiplier. We just did. This is the appropriate multiplier. Now, what if my sequin was completely flat? Well, then fx and fy would have both been 0, which would have meant 1 times this, and that's exactly the area we should have gotten. So nice formula. So now I'm going to show you how to use this to answer the question. So going back to the top here. So the problem starts with, I have a surface, call it Z as f of x, y, over the region in the xy plane. That's what it is. So what we need to do is add up all of the individual sequins, if you will. So I'm going to do the double sum of this. So a reasonable estimator of the area would be the sum of the fx squareds, fy squared plus 1, delta x I and the delta yj. We do the double sum. If I take the limit as the norm of the partition approaches 0, what's the norm of the partition? The largest such product of delta x and delta y. Then I eventually get the area equals, therefore, the double integral of this. And I'm going to write generically dA over the region in the xy plane. Remember, this says the region in the xy plane, that's the shadow of my blanket that I fluffed. The region in the xy plane, that's two-dimensional. That's where I'm going to get my limits from. This is my integrand, and dA means I'm either going to integrate dy dx or dx dy. That choice is yours depending on how the problem's described. But this, my friends, is the formula for surface area. It's right there. That's it. That's not a complicated formula to use at all. But what you're going to find is, depending on what f of xy is, it is often going to be the case because you have a sum of squares plus 1. That integration can be very, very difficult. Okay, remember, there's no chain rule factor in 3D. So if I've got x's and y's under a square root, that can be really difficult. But it's often going to be the case where we will be able to use polar. So we're going to look at that. All right. So let's start with a simple one. Well, simple is relative, I guess. Let's consider we're going to find the surface area of, oops, I found enough room here, of f of xy equals, let's say, 36 minus x squared minus y squared bounded by z equals 0. Z equals 0 is the xy plane. So I have the xy plane cutting something off. So what does that look like? Well, this is a downwards opening circular paraboloid. Looks like that. Okay. Well, maybe I should do this because that's behind. There we go. Give a little more dimension there. So I have the downwards opening gumdrop. It's going to intersect the xy plane, and it's going to intersect the xy plane we're going to see in a moment as a circle. So I want to find the surface area of this thing, not the circle. No, the circle isn't the surface. That's the surface. And this surface goes forever and ever and ever and ever. I just happen to be cutting it off with the xy plane. Okay, so I need to determine what is my region in the xy plane. That's one of the first things I need to do. So what is this? Well, the xy plane z equals 0. So that means 36 minus x squared minus y squared equals 0. What does that give me? That gives me x squared plus y squared equals 36. So the region in the xy plane, I'm bounded by a circle of radius 6. Beautiful. Okay, that makes things very nice. So now what we need to do is do what's called the surface area parameter. That's the square root of fx squared, fy squared plus 1. That's called the surface area parameter. So let's find that next. Okay, and we give this, I'm going to give it a formal name in a minute. So when I do the fx, I get negative 2x. When I do fy, I get negative 2y. So when I square these, I'm going to have negative 2x squared, negative 2y squared plus 1, all under the root. And that's going to be 4x squared plus 4y squared plus 1, all under the root. That's what we call the surface area parameter. That's going to go in my integral. So here's the way we usually describe this now with formal notation. I just use the word area. But actually, we generally use a capital S. A capital A is area. We always use that. But we usually think of that situation as being a two-dimensional area. So if I said, what's the area of a circle? You'd say, oh, pi r squared. But if I said, what's the surface area of a shape? You're going, oh, that's not the same as a two-dimensional area. So we usually write it like this. Capital S equals the double integral over the region in the xy plane. Again, fx squared, fy squared plus 1 dA. We call this here, the entire quantity, we generally call ds. D with a capital S, because I'm doing the integration of dA, of ds, just like here, that refers to the area. So dx and dy, right? They're the pieces we use. So this quantity is generally referred to as ds. So if asked, what is the surface area parameter in this problem, you would say ds equals 4x squared plus 4y squared plus 1 dA. And that's the part that's going in the integrand. And this is going to be a really common thing because we use this in several other contexts over the next few weeks. We're going to have to calculate, again, the surface area parameter to answer a different type of question. Okay, there's a whole lot of different questions we can have that involve surface area where the answer isn't just the surface area. So let me go back, let me erase this so I can set up my integral now. Okay, we said the region in the xy plane. So right now my problem looks like this. S equals the double integral of the region in the xy plane of 4x squared plus 4y squared plus 1 dA. Great. The only problem is my region in the XY plane is a circle. And that makes those limits a little bit tricky, but I can do it. But how do I integrate that? This has no antiderivative. No matter how hard I try, I can't integrate. Well, what about a trig substitution that only works with one variable? But I can do polar. Okay. You can't do a trig substitution like you did in Calc 2, but polar is kind of your trig substitution in higher dimensions. So knowing that r squared equals x squared plus y squared, then what does that make this quantity here? If I write it right here, this is 4 times x squared plus y squared, is it not? Aha. So that tells me everything I need to know. That means this is going to equal 4r squared plus 1 under the square root. But then what do we add at the end here? Do you remember from last day?
R dr d theta.
R dr d theta. And I am very happy with that because if that's my u, there's my du sitting right there. So this is going to actually be a simple u sub. Now, what about my limits of integration? Your region in the xy plane is this circle of radius 6. And since it's the entire circle, theta is clearly going to go 0 to 2 pi. R is going to go 0 to 6. And that integration is just not that bad. Okay. Now, I don't like the square root. Today, my Calc 1 class started u substitution. And so they figured out really quickly that when you had square roots in the integral, change it to a fractional exponent because it's too hard to interpret otherwise. So let me rewrite this then. Okay, the double integral 0 to 2 pi, 0 to 6. I have 4r squared plus 1 raised to the 1/2 power, and I have my dr and d theta. Clearly, that's going to be my u. So I'm going to actually physically write down the substitution. I'm just not going to change anything yet. So if I said, let's let u be 4r squared plus 1, then the du I need is 8r dr. I have an r. I need it to be 8r. Oops, sorry, I didn't write down the r. Okay, so what I'm going to do, there's my 8r. All right, now I have exactly what I want, but I just made my integral 8 times too big. So if you remember, you compensate out here. You can always do this with constant multiples. You can't do this with functions or variables or anything else, but with scalars you can. So this is now of the form u to the 1/2 du. And if you need to off to the side, the integral of u to the 1/2 du is 2/3 u to the 3/2. If you have to do that off to the side, go ahead and do that. But you can just go ahead now and integrate this. All right, so u to the 1/2 du, I'm going to get 2/3 u to the 3/2 integrated from 0 to 6. And then I put the d theta on the outside. What about that 1/8? It's still there. And I certainly could have cleaned that up in one step. We will clean that up now. So that's 2 over 24 or 1/12. And how about here? When r is 6, then 4r squared plus 1, that would be 145 to the 3/2. When r is 0, then I have 1 to the 3/2. I like that. That's a constant. It's an ugly constant, but it's a constant. So if you remember, my answer is just going to be the constant times 2 pi, or if you want 2 pi minus 0. What about the 1/12? Well, it's 1/12 times 2 pi times that. So I'm going to write it as pi over 6. That's probably the best answer. 144 is a perfect square. 145 is not. So that can't be simplified, unfortunately. In fact, 145 doesn't have any factors that are perfect squares. So that's about as good as I'm going to get. Yes, it's ugly, but it wasn't all that hard, which is really kind of cool that we were able to do this. Okay. Does anybody have a question on this so far? Just if you have anything, just go ahead and blurt it out right now. I don't want to have to change the screen. Okay, let's do another. I like surface area because it gives us a really good application often of polar. You don't always change surface area into polar, but you find that it's very, very common. All right, let's consider, we want to find, let's say, let's see if I can draw this well. I want the top half, this isn't very good, I know, but I want the top half of a sphere. So in other words, I want a hemisphere. I have the top half of the sphere. Let's say it's x squared plus y squared plus z squared equals a squared. I have a sphere of radius a, but I just want the top half. Okay. Now we know what the surface area of a sphere is, but that's good because then we can compare it to whatever we get as a final answer. So I would like to do this. Well, in order to do this, I need to solve for z. So z is going to be the square root of a squared minus x squared minus y squared. And because it's the top half, I don't have a plus or minus. All right. So I have a hemisphere and I want to find the surface area. That means I need to take a couple of partial derivatives. So if you'd like, think of this as your f of x, y. Okay. So first thing is, what is fx? Well, this whole thing's being raised to the 1/2. So that's 1/2. This is to the -half, and then the chain rule factor being -2x. And so that would be -x over the square root. Okay. Fy, well, Fy is going to look real similar, isn't it? Because they serve the same purposes. So I can be kind of lazy here. Fy is just going to be this. I mean, you don't have to be a rocket scientist to realize, oh, I'm doing the same thing exactly. So finally, my surface area parameter, and I'm going to write it formally. ds is equal to this squared plus this squared plus 1, all under the root, integrated with respect to a. Oh boy, that looks absolutely terrifying, doesn't it? Or does it? If I put this all over a common denominator, won't this term here become a squared minus x squared minus y squared over a squared minus x squared minus y squared? And if I add this to this to this, I'm going to get some serious canceling, aren't I? What will that leave me with? Anybody? What will I have on top? This plus this plus this. Does anybody see it?
Is it just a squared?
Just a squared. I like that. Boy, that's going to make this a lot simpler to evaluate. So that leaves me with just the a squared. But I'm going to be even lazier than that. That a squared is sitting in a square root. So can I just write it as a? Can I just do that? Yeah. Oh my gosh. Boy, that turned out to not be that terrible. Okay, it doesn't look great, but it's not the worst thing. There are way worse things in life. Okay, so I think I'm going to need to erase this stuff. Now, what is our region in the XY plane? This is something we have to consider. Okay, remember it's x squared plus y squared plus z squared equals a squared. So our region in the XY plane, that means that the z is 0. Remember, because I said the top half. So that means it's just, I'm sorry, this isn't equal. That means it's just x squared plus y squared equals a squared because z is 0. So my region in the XY plane is a circle of radius a. Remember, it is a sphere of radius a. So the XY plane would be that circle. Okay. Well, right now we have that the surface area equals this, okay? Well, my region in the XY plane is a circle, and I see an r squared sitting right there. So again, this one is ripe for polar. In fact, if I didn't do polar, this one would be probably impossible. Okay, so let's make this into a polar integral. So we're going to say this is equal to, again, 0 to 2 pi. It's a circle of radius a, so it'd be 0 to a. This would be a over the square root of a squared minus r squared. Okay, because x squared plus y squared is r squared. And once again, r dr d theta. Now that looks kind of scary again, but like before, if I choose this to be my u, then I basically have the du sitting right there. So off to the side, we say let u equal a squared minus r squared, then the du is negative 2r dr. And again, we see this common theme. So if I put a negative 2 there and a negative 1/2 here, then I'm going to rewrite this quantity in a more user-friendly format. This now becomes negative 1/2 a times, and in fact, you know what? Let's just take the a on the outside. Let's just get the a out of it because the a is a constant. So how about negative a over 2? And then that leaves me with a squared minus r squared to the negative 1/2 times negative 2r dr d theta. Okay, algebraically, this and this are absolutely the same. So again, off to the side. Remember, all the calculus students struggle with this, but there's an absolute in mathematics that you cannot mess around with. If you change the variable in a definite integral, then you have to change the limits. There is no such thing as a definite integral where you substitute back. That does not exist. That's an operation that cannot exist. Any more than I'm doing this in polar and I'm going to switch it back to rectangular. What? No. A definite integral is a scalar. You don't ever change back once you change a variable. So therefore, unless you want to do all the limit changes, that can get kind of messy. So it's probably easier to just off to the side say, I've got u to the negative 1/2 du. That antiderivative would be u to the 1/2 times 2. Okay, great. This is of the form u to the negative 1/2 du. So my antiderivative is going to be 2 u to the 1/2. Evaluate from 0 to a, and now I'll just fill in the blanks. I'm lazy. I don't like doing long-winded things that aren't necessary. But at the same time, if I'm going to put an equal sign between these have to be equal. If you change the variable, you have to change the limits, period. There is no exception. And if somebody showed you something different, they were trying to get your money, probably, or sell you that beachfront property in Arizona or something. Nope. If you change the variable, you got to come up with the new limits. And that's always correct. But in a double integral, that's just a lot of extra work. So just know what the antiderivative is, and then this equals this. No worse for wear. Now, what do we got next? When I evaluate this at a, I have a squared minus a squared. That's 0. When I evaluate this at 0, I have a squared to the 1/2 power. That's just a, because a is a radius. There's no absolute value there. So I have 0 minus 2 times a. So that's just negative 2a. I have negative a over 2 times negative 2a. That's a constant. Well, that's a squared. Is that right? Did I miss anything? Yeah, that's a squared. Make sure I didn't lose anything. That's a squared. And now I'm going to multiply that by 2 pi. So this is 2 pi a squared. That's kind of an odd answer. Oh, by the way, what is the surface area of a sphere of radius a? Isn't it 4 pi a squared? And we just did the hemisphere. So 2 pi a squared. Yeah, that's exactly what it was supposed to be. And again, the integration when I converted it to polar just wasn't that bad. A u substitution is probably the hardest integration you're going to do. Now, last day I said occasionally it comes up that you might have to do an integration by parts. Okay, occasionally comes up. But generally in Calc 3, you're never going to see things like partial fractions decompositions or trig substitutions because those only apply when you have one independent variable. Okay, those you'll see a little bit maybe in a differential equations class, because that's all about integration. This class isn't all about integration. We're doing a lot of applications, but our applications tend to be, a little lower level stuff. Okay, now this is surface area. I could do examples all day, but they're all going to be exactly the same thing. You set up the problem. The most important part is creating your surface area parameter. Now, I'd say probably the majority of the time, you're going to end up doing a polar substitution because the nature of your surface area parameter, the fx squared and the fy squared often create this situation. But it's also totally possible that it's rectangular. On the quiz that I've given you on this stuff, I know that one of the integrals is purely rectangular. You don't have any reason to change it to polar. But other integrals, it makes perfect sense because of your circular regions. Okay, so I'm going to stop there because that's all I need to get to. And now I want to talk about the exam. Okay, now we have an exam. Make sure I got it in front of me. And it's on Tuesday, the 13th at class time. It's all the same conditions as last time. The exam, just to remember, covers lectures 8 through 15. So that's the same as saying it covers quizzes 8 through 15. Now, the first exam conveniently ended at the end of the vector stuff. Remember, we did tangential and normal components of acceleration and all that stuff. Then we started with surfaces, domains, and continuity and limits. Absolutely a different thing. So this test does not involve, I don't think, anything vectorish. The only thing that you're even remotely vectorish is on your Lagrange multipliers, your gradient vectors. But that is just to create the equation. So you're not really working with vectors, I'm pretty sure, on this test at all. I'm looking at everything down here. So the test starts with the functions of several variables and goes through the introduction of double integrals. That's the quiz today. Now, what's interesting on the quiz that was turned in today, I got some interesting answers. Now, I went over a couple things specifically. When you are doing a multiple integration, you do the entire multiple integration. You don't do, I'm going to take this and do this as a separate problem and come back. That's not a thing in integration. You just integrate straight through. But the other thing was, I found was interesting. In Calc 2, on the first day of class, Calc 2, I do centers of mass. Okay, you guys remember doing that kind of stuff, centers of mass. Centers of mass are really simple single integral problems. And on the first day of class, I think I had 6 people. This is the first day of Calc 2. I had 6 people turn in triple integrals to find their centers of mass. Triple integrals, which, by the way, we haven't even defined or used yet. On the first day of Calc 2, gee, I wonder where they got the triple integrals. Well, a really, really, really crappy website, clearly. It's not even possible to do that problem with multiple integration, yet they had triple integrals for a single integral problem. Nobody came even close to an answer that was meaningful, and they all got zeros and they all got reported because they obviously went to the internet and cheated. On the first quiz of Calc 2, I had 6 people cheat. By the way, all 6 of them have long since dropped the course. You have to cheat on the first quiz, you're in big trouble. Well, guess what? I had people turn in the second problem here with a triple integral to find the volume. First of all, you don't use a triple integral to find a volume, period. That has no meaning whatsoever. We're going to learn triple integrals soon. Triple integrals are only used to find centers of mass. And then when we get to what's called spherical coordinates and stuff, nothing we're doing in any way can be done with a triple integral or even suggested. So when I have people turning in a quiz with triple integrals, when you haven't even defined one yet, yeah, it looks like you went to a really crappy internet website and said, let me type in the question. And the fact that they give you a triple integral means I wouldn't trust anything that website put out, because you can't do this with a triple integral. But I got the right answer. No, actually, you have an incorrect setup that luckily produced a right answer. There's no triple integral when you're doing a volume problem of a rectangular coordinate system. You can't do that with a triple integral. Besides which, we haven't even learned that yet. So probably shouldn't have turned in a triple integral. And if you did, you should be embarrassed, because you did something that you've never actually seen in your life and you turned that in. Remember, going to the internet is called plagiarism. The crime of plagiarism is punishable by expulsion from school, not failing the quiz, expulsion from school. And the Mesa College has been really, really serious and ambitiously and aggressively pursuing people who are plagiarizing. So don't do that. Now, I know it's after the fact, but I couldn't believe that anybody actually turned in a triple integral. Yet I got several of them. Yeah. So starting from the beginning, what is going to be on the test? Well, you guys all have the practice tests and you've all had the quizzes. Now, redoing the quizzes would be really, really wise, because I don't care if you got a perfect score on the first quiz. The first quiz came from a lecture on February 25th. February 25th was a long time ago. And most of the material was before spring break. In fact, no, I'm sorry, all of the material was before spring break. So going back over stuff would probably be wise, simply because, you know, a lot of time has passed. So you know what's on the test. So I want to get into some of the specifics and how the test is broken up and organized, okay? Because that's really, really important. You already know what the questions are. That kind of goes without saying. You're going to be asked, you know, what's a domain? I'll give you a simple limit problem. Okay, now let's get to the meat and potatoes. The most common type of question, or I should say the biggest question, not the most common. I'm going to give you a function. And I did this on the practice test. I'm going to give you a simple function. Let's say f of x, y, z, and maybe it's, you know, x squared, e to the y, z. I don't know. Let's just keep it simple. I'm going to give you something like this. And now I'm going to ask you a million questions on it. I'm going to ask you partial derivatives. I'm going to ask you equations of planes and things like that. Now, I'm going to ask you for normal lines, equations of planes, doing tangent plane estimations, all of these things. And let's say the point we're going to use, let's keep it simple. Let's say we're going to use 2, 0, 1 as our happy point. Okay, so what sorts of things can I ask you? Well, like I said, equation of the plane. In fact, hold on one second. Let me look at my practice test here. What did I ask you? Yeah. Lest we forget. Directional derivatives, okay, equations of tangent planes. I might ask you to use the tangent plane to estimate, how about f of 1.98, 0.03, 1.04. In other words, something very close to happy point. And so when you found your equation of the tangent plane, you did all those things. It's all of the same thing over and over and over again. So I caution you to be very, very careful when you're taking your partial derivatives. But partial derivatives are going to be a dominant theme on this exam, because that's almost all we did on this exam. After discovering continuity and domain and limits in the first lecture, and then doing the integration in the last lecture, I think probably 6 of the 8 lectures are partial derivative related. So what else might be on there? Well, I'm going to ask you an extrema question. I'm going to give you a function of x and y and say, find any extrema and or saddle points. And that's the one where you use the Hessian. I'm going to give you a Lagrange multiplier problem and say, use the Lagrange multiplier. Now, on the Lagrange multipliers, most of you guys did a really good job, but there was one common error that appeared on, I'd say, more than half of the quizzes. When I use a Lagrange multiplier and I found my value is, 1,000,000. Is that the maximum or is that the minimum? I don't know. Well, 1,000,000's really big. It's got to be. No, that's not how it works. How do I know if it's the maximum or the minimum? You take any point on the constraint. Now, I want to make sure everybody understands this part, because this is the one thing we got in trouble as a group. The Lagrange multiplier part was beautiful. So I'm going to make a little simple picture. I have a Lagrange multiplier problem, and I found something. I found one point. That point is either the absolute maximum or it is the absolute minimum, period. Now, if I found 2 points and I got different values, then one of them is the max and the min, and you actually like that. You don't have to do anything. But I gave you a value. If it's the maximum value, if it is this, then every other point on the constraint, think of this as the constraint, every other point on the constraint when evaluated would be smaller than this. Every other point. Therefore, you only need to test 1 point. If what I found was the absolute minimum, then every other point on the constraint would be above it. That's it. But that means I have to choose a point on the constraint. The problem that we had is people were doing tests, but they were just picking points at random. In fact, I got a lot of people testing 0, 0, 0. That's my favorite point to test, but 0, 0, 0 wasn't on the constraint. So if I test a point that's not on the constraint, more often than not, it's going to lead to the wrong conclusion. So you have to choose a point on the constraint. How do you do that? Well, the way I always do it is pick 2 of the variables to be 0. And there's an infinite number of choices, but I always pick 2 of the variables to be 0. Then I don't have to mess around. Then the third one's kind of automatic. But again, if I choose a point that's not on the constraint, then any conclusion I get is not valid because I'm basing it on the wrong information. But for the most part, your Lagrange as a group, almost everybody did the bulk of it correct. They weren't always sure at the end, but there must be a test. You can't get a value and decide if it's the maximum or minimum based on no evidence. You actually have to test it because you really can't know. I mean, there's too many variables going on. On the Hessian problem, okay, same thing. You can't know if it's a maximum or a minimum or produces a saddle point unless you actually do the Hessian. So make sure that you've got those things down. And yeah, that's it. Now, there will be no polar on this test, right? That's the first lecture for exam 3. So if you find yourself wanting to switch things into polar, probably isn't a great idea. Now, you get to bring, of course, 3x5 card, both sides. No matter how many times I say that, people squeeze everything on one side. Theorems, formulas, definitions that we've covered in this class. Well, have we covered any theorems, formulas, or definitions? Yeah, I think we've covered a few things that were new to you. At this point, you know how to take a partial derivative. I'm not worried about that. But what about a directional derivative? What are you actually doing in a directional derivative? Remember, you're evaluating the gradient vector at the point in question, and you're doing a dot product with the unit vector in the direction you're going. And that unit vector part's critical because a lot of times people will do it and they forget it's a unit vector. Okay, so we want to make sure you have that. That's a formula. What about the Hessian? Okay, what is the Hessian? That's a formula, but it's also a theorem. So I've got fxx, fyy minus the square of xy. And by the way, I'm not going to give you a Hessian problem where the Hessian is 0, because that means it's inconclusive. That's just evil. It's greater than 0 or it's less than 0. Okay. Everybody, when it's less than 0, what do you have? That's the easy one. If it's less than 0, you have a. It's what you write, when you're on your horse, you're looking for
Saddle
points. Saddle point. A saddle point, XYZ. Saddle point is a coordinate. It's an XYZ. The reason you like this one is you don't have to do anything. It's the saddle point. What if it's greater than 0? Now you got to do a little bit of work. First of all, you have an extremum. But do you know if it's a max or a min yet? I have an extremum, but is it a max or a min? Now, if this is greater than 0, it automatically means these guys are the same sign, because if these were opposite sign, I'd be less than 0. So they're the same sign. But for it to be a max or for it to be a min, what must be true? Think of concavity. In Calc 1, if I am concave down at a critical number, I have a max. Concave down meant your second derivative was negative. So it's a max if both of these guys, I'll put are less than 0. A little arrow here. It's a min if both of these guys are greater than 0. That's one of the things we sometimes forget. Now, the max and min are z values. That doesn't change from Calc 1. An extrema is a value. A saddle point is an address. Okay, a saddle point's got to have 3 coordinates and extrema is 1 value. A lot of people still get these confused. And in fact, I get people giving me ordered pairs for both of these, which is really confusing. This is a scalar. This is a point in 3 space. That's all it is. Now, absolute versus local. I'm almost to the point where I don't care if you get that right, although you should get it right. Absolute or local just has to do with the behavior of the function. That's not calculus. If you said, all right, let me let x or y increase without bound, positively or negatively. If I can show this thing goes up forever, then any maximum's got to be local. If I show this thing goes down forever, then any minimum's got to be local. That's it. So sometimes it's as simple as looking at the degrees. So that the local versus absolute is the least important. Getting max versus min, yeah, that's kind of huge. Okay, so that's what's on the test. As like before, you have 2 hours. You won't need 2 hours. If you can think of anything Like the obscure thing, I'll get a lot of emails saying, is this legal? Can I put this on the test? You can't put examples because now you have open book once you do that. You can't put old calculus formulas from other classes. For example, I can't remember all my derivatives, so I'm going to write them all down. No, this is Calc 3. If you don't know your derivatives inside and out, you're in trouble. you shouldn't be in a Calc 3 if you can't do the derivatives. My Calc 1 students can all do all of their derivatives without thinking at this point. We're in week 9. They can all do every one of the 20 plus derivatives they've learned pretty easily. Even someone to even cotangent the guy. Okay, we're not worried about obscurity, but you should be able to do derivatives of sines and cosines and e and log and things to powers. That's really not an issue. Nobody here's run into too many weirdnesses in that regard. Okay, I'm going to stop there. Now, if